So, folks, I've been asked by someone in the lecture hall for further instruction. I've been notified that the link did not work. It's very possible. Now I will show you how to fix the link. You go on Google and you type srg2 Orazio, and you will find a GitLab repo. And this is the repo for Orazio. And then, if you want to have detailed instruction on how to build a robot yourself, there is srg2, Martino, and then I think that Luca prepared the page, so Martino Iocchi, which is not a robot, no, it's not the family name of the robot, but it's a page with all the instruction, part list, build software, and so on and so forth. Okay, guys? If you want, this is absolutely not mandatory, nor anything. If you like to have fun and to play with these sort of things, this is an option. But my suggestion would be start with the simulator. Okay? Then there was another thing that I was doing in the interval, which was recording a data set of this lecture hall, because apparently the network for a moment worked. Now I will have to find a harder solution for the network because it's definitely too brittle to operate with the robot in the class. I mean, basically nothing is sufficient for the network to collapse for the Wi-Fi, and so there's not much I can do right now. Believe me that whatever you have on the robot is like more or less what the simulator gives you. Okay. You will receive in a while a software by me and by my folk. You will receive a repository, an entire workspace with instructions to be built. The instructions will be uploaded onto the repository of the course, together with the repository itself. All you will have to do, well, is follow the instructions, and then you will have basically a decent configuration with which you will be able to run cool things. For instance, you will be able to run dataset, to run SLAM, to get a map, and to run our navigation system. Now, what we will be doing in this second part of the lesson is to show you some additional thing, and I think you're now able to write a simple publisher subscriber. This is what I've shown you already. And now let's see, I don't know, how to define a message in ROS. And as always, I don't know, I mean, I feel like kind of, how to say, too simplistic in a sense, because this is something you could do it yourself. I'll show you why. ROS defining a message, GPP. ROS tutorial. Huh? And then you find this tutorial unrolled for you. Okay? So, given that is sort of, how to say, super well documented and is a task for you, I'd rather, instead of showing, okay, I have to open a file and to do this, I'd rather like to do some sort of inverted classroom from this point of view. So you try to do it, and then next time you tell me the problems. What is the thing? ROS tutorial creating a message and a service. Okay? Is that clear? Like what I'm asking? Much better this way than me going there and losing time, because I'd like to finish in a reasonable time so that you can start with projects and I can start thinking about projects. But once you have are able to define your own messages, which in the end boils down, okay, I can't refrain myself from doing so, boils down to edit a text file which contains the message definition, which is like something like that. It's message. ROS message, ROS CD, sensor messages, CD MSG. There's a directory called MSG. And then, okay, this is a lot of comments, but all what you are doing is nothing else than defining a struct. And then the rest, of course, all these comments here are for confusing you. But in order to define a message, you just have to list the fields of a struct, and that's it. And then you have to tell the build system, please, there is this message. From a compilation point of view, and I think it's the most important thing, you should know that the message is not code. The message is meta code. It's code that is generated to produce code. Because once you define a text file, let's say, Ctrl-Z, where was I that I created the package? ROS cd, source, my new package. If I would create the directory msg, kdir msg, I would create a message, mkdir msg. I have the directory with the message, cd msg, emacs my message. To msg, I think how they are made. Yes. Okay, int 64. My int float. What? Values. An array of values. Okay? I've defined my message. That's all. Nothing spectacular. Then I have to tell the build system, hey, dear build system, there is a message in this package, please include it. Do you have questions, guys? Or no, I'm asking because I know it's just like your business, but I just wanted to know. Okay, then we have to tell the build system somewhere we will have to edit the CMake files and something to say, hey, dear man, there is a message file in this package and it's called my message. And what we will have to do is to do cd cd source emacs CMake. No. Oh. I deleted my new package, I think, because last time I was creating a package. I suspect that I destroyed the package, the package itself. Yes. Remember I was creating this my new package, I think I destroyed it. But, so, cutting, package, my other. Package. My other panel, ROS cpp, cpp, very good. My other package, the MSG, Emacs my message, MSG, int 64, value, float 32 values, or numbers. Okay, now this message gets compiled into a C++ class. But in order to get compiled and into a Python class, because ROS admits also Python bindings, but from this means that there must be a tiny GNOME that goes there and produces C++. This is the Lisp meta package of ROS that reads this business and produces classes that you don't see, but they are there. And these classes include the serialization mechanism, because a message is introspection. I give you a message and a message should be able to tell, it flows over the network, okay, I'm a message, I have an int, which is called this way and this way and this way. And it handles all the serialization business. This is done for you for free. Remember that every package in ROS defines its own namespace. So once you want to include a message, you have to say always name of the package, column, name of the message. Okay? That clear? There is the convention of using camel case for the messages in ROS. Okay, now compile these messages. cd dot, cd CMake list. I think there will be, I have to uncomment, add message files. How did I call it? My message. Do I need to add services? No. No, 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 no. And then there will be message runtime. In the add build depend tag for message generation. You see? Package XML. Message generation. Message generation. No. Okay, of course I never remember these things because you can't remember these things if you don't do them daily. But if you follow the instruction, presumably you will be able to compile this thing. Let's see, let's see, let's see. Generate messages, RES. Region. Dependency. No, I think I'm done. Add message generation for every package. I added add message runtime. Catkin depends. Che me frega. I'll try this way. Catkin build. Something wrong. Why? Notes, make comments, add message files. Probably there will be something to be done. Message generation. What do you want? Numbus is not a legal message field, okay, because probably I have to use a Java version for the message. What was it? Message, my message. Probably it wants this. Done. Okay, was it hard? No. You only have to read carefully the documentation, which I never do, and then enable the right things. Now we have a package with a message, and it's not uncommon in ROS that you have packages which are only consisting of messages. Example, standard message, sensor messages, and so on. There's no processing utility, there are only data structures. They make sense. They make a lot of sense, because if you want to decouple, for instance, all possible sensors, all possible cameras from their driver, it's not that every camera has to define its own kind of image. You just define the image, this is the image, be happy with that, and then you have the drivers producing their own thingy, their own value for the data, but not their own type for the data. Okay? Very good. All right, now, this was something that I needed to tell you. Now, the messages work this way. I couldn't refrain myself from sharing this with you, but also the services work in an analogous way. Now, I invite you to learn and implement a trivial service by using the documentation, because I think it's out of the scope of no, going through the API is something that they don't think it's super brilliant to do. Okay. Then let's now, because it's compiling all my workspace, which is huge. Now easily this, impress. Let's go to a more interesting lesson, which is setting up a robot. So now we look at ROS, and what do we have? We have an ecosystem of little programs. One little programs that listen the camera, one little programs that deals with the mobile platform, another little program that deals with the laser and presumably produces the laser data. And then they are happy with that. And then we write programs that send and receive messages from them, and then we are happy with them. That's one thing that we are losing, and which is how these devices are put together with each other, right? Now, this robot, the one that I have on the table, has a very specific configuration. It has two wheels, has a laser scanner mounted on top, okay, and the laser scanner is mounted at a specific angle, from with respect to the wheel axis. If I would rotate the laser scanner of 80 degrees or 90 degrees, then I would sense different data with respect to the one that I'm sensing with the laser looking for. I imagine that you have a manipulator or stuff like that, and then there it becomes even more complicated. I was already mentioning that. No? Now, nominally, all devices that you might find in ROS, they are seen as sources of data and sinks of data. They typically produce a topic repeatedly. They produce on a topic a message of type, the right type, and they subscribe to another topic the commands that you want to send to these sensor or actuators. If you want to see classical sensor messages, they are defined in the package sensor messages. You can do ROS message, show, sensor messages, whatever, and then you find the data contained in the message. If you go into the directory of the message definition, you will be also able to see the source with further explanation on the messages themselves. Now, interestingly, now let's pick up one of those. Okay, one message of the sensor messages. ROS CD, sensor messages, and I'm in sensor messages. I go then into the directory messenger. Plenty stuff, no? There's battery state, camera info. What will be battery state? What do you guess it will be? Battery state. Of course, it's all humongously and insanely bloated, but it's a battery state. Right? That tells you also the technology, all sorts of things. You know, they are a little bit redundant sometimes. But this is the battery state. Voltage, current, charge capacity, design capacity, percentage, power supply status. Of course, the messages, standard messages, they have to be as general as possible, and that they have to include all possible information you want to have. Let's see another sensor messages. Camera info? No. Image. Image will contain the header, which we will discover soon, the height, the width, the encoding, so if it's JPEG, PNG, whatever, and then basically the data of the image. Then this big endian is a way of a flag that tells you how it's stored on the disk, and step tells you how many bytes you have between one row and the next on the byte string. All right, that's an image, and so on. Laser message, sensor message. All data, they have this funky thing over here, header. Now, there's a thing which is called header, and it's called of type header, and which is called header. What is an header? An header, ROS message, shove stud messages, header. Oh, a header is a fragment of data made this way. There is a sequence number that denotes the an incremental number that increases as the messages are generated. You shouldn't rely on it, even if to me it's extremely useful to monitor if there is the packet loss in the network. And so they removed it from the next specification of ROS. There is a thing which is called a time, and there is another thing which is called a string, which is a frame ID, and this is the interesting bit. Now that you are all, let's say this way, enough used to robotics, you exactly know what a reference frame means, right? Exactly. And frame ID, it's a string, and it's a name of a reference frame where you have mounted something. Clear? Very good. Now, we have and so each sensor data, that datum of a sensor, each image and whatever, carries attached the timestamp and the frame ID, not the position. The position is not the responsibility of the program that is reading from the camera, right? The position, that's a stupid program that reads from the camera. It doesn't want to know about the rest of the universe. Clear? So it just says, hello, I am camera 1 frame, attached every time. Clear? Very good. Now, going back to the list. As I was saying, how to access a device in ROS, the mobile base in ROS, like the one that those in class have seen, basically publishes one message, not message odometry. And how do you see? What do you have in odometry? You have the global position of the robot obtained by the odometry integration. You don't have the increments. You have the global position. Why don't you have the increments? Because if I send you the integrated position and you lose a message, there's no issue. But if I send you every time the increment, you lose 10 seconds of increments and you're completely lost. So if I just send you the integrated position, you will be anyway able to recover the increments because you take one, you take the next, then you calculate the difference. Okay? This is what it produces, and what it subscribes to is geometry message twist. That it's an angular and rotational velocity. All velocities and all data are in 3D by definition in ROS, even if the robot is 2D. But this doesn't really matter because you just convert from 2D to 3D and you pass it through there. And then in your piece of program, you will have also to take the 3D, and if it's moving on a plane, you have to basically ignore the remaining 3D components. Okay? Stage, we have seen it already, and I have given you plenty of demonstration on how to use it, and this slide contains a list. But what is interesting now is that we have, not in the simulator, but in the real robot, once you construct a robot, there are 3 things that you have to do. First thing, you have to assemble it. Second thing, you have to be sure that you assembled it correctly. Third thing, you check the power supply. And then this third aspect, this comes from my experience. There is one way you can break things, is messing up with the power. If you don't mess up with the power and we just play with the signal lines, you can't do too much damage. But if you mess up with the power and you have fun in inverting the power supply or doing some things, you can ruin the hardware basically. No? We are at 12 volts, we are not at 50 or 300 volts, so there's no fire, even if you can make a H-bridge exploding, but that's not something massive. Once you have done that, and you are sure that the firmware is matching the hardware, so that when you say move the right wheel, it moves the right wheel, and you really read that the right encoder is moving, and so on and so forth. And once you test every single device, every single sensor, prior mounting it on the computer, all integrated, you have to do everything on a laptop or on a larger computer comfortably, trying every device on the power supply that you will be using on the robot, but attaching it to a computer where you can work. You never use a Raspberry Pi to do the final deployment. You never, ever program directly on an embedded system and compile directly on an embedded system. Maybe the Raspberry Pi for some small program could work, but on average, You don't compare, you want to be comfortable. These are my suggestions. So now we are at the situation that you have your computer and you have all single nodes, all single aspects that control the robot or control the actuators and read from the sensors that work. And that they work stable. Okay? They need to work stable. So you have to let them running. I'm talking for when you will be going to work. And these are, believe me, that these are things that make the difference. In order to make them running, you stress them. You put this platform, you put your thing, you put it on a basket, and then you let them attach to a stabilized power supply, and you monitor the current while it's moving for half a day, up, down. You create a simple program that sends actions to move the joints and so on, and you monitor the behavior of every driver and every sensor for half a day or for a day. At the end of the day, you don't need to have any memory leak or any other thing that messes up. And in this context, it's really worth to think to work with the W error. So every warning is an error, okay? Because in the deployments, it will crash. So if it's something you have never seen, you're forgiven. But if it's something you have seen and you ignored, then you're not forgiven. Okay? Not by me, by whoever will give you millions to build this little robot or whatever, right? Okay, now we are at this situation. We have our hardware working and our CPU is very, very low. It's very low because to read the data from a platform, for reading from a serial line and for reading an image, I don't want to have 90% of all my 10 cores because otherwise this robot, once on battery, travels 10 meters and dies. Okay? All right, now, all these devices, they are mounted with respect to each other in a certain way. And so what you have to do is to construct the Davenit-Hartenberg chain of your platform in general, right? Like the configuration of your platform in general. But in case of stupid robots like this, where there is no moving part, you don't even need that. Because all you need is to define where is a reference frame for the base of the robot, and then you can locate all the sensors in the game. In order to make the situation a little bit more juicy, we could imagine that we have a camera mounted on a pan tilt unit, which is 2 joints, right? No? Pan, tilt, 2 joints. It's also simple, the kinematics, both direct and inverse, and so on and so forth. And also we can assume, these 2 joints, this pan tilt unit on top of the pan tilt unit, it's not that you buy a pan tilt unit and you leave it there as it is, right? Maybe you want to mount a laser on the pan tilt unit, You are expecting a camera. No, maybe you want to mount a laser on the pan tilt unit because you want to be able, with a 2D laser, to get 3D scans. Okay, guys? Agreed. Now, very good. Now, once we have this spectacular machinery, and we have it mounted on the robot, we would like to, the essential thing is basically to be able to simulate. So we would like to be able to determine which sort of laser scan the robot was seeing, assuming that the robot was in a certain location of the environment, and that the pan tilt unit was mounted in a certain way, right? And so basically this is a matter of direct kinematics. Okay? Now, the laser will tell you what is the kinematics of this robot. Well, we have the mobile base, the origin of my robot. And then on top of the origin of your robot, at a certain location with respect to the origin of your robot, you will have another reference system, which is the origin of the pan tilt unit, the base, the block of the pan tilt unit, right? And then depending on how it's made, the pan tilt unit, you will have one, like maybe the first reference frame, which is turning in this direction, and then the second reference frame, which is turning in this direction, no? Panning, tilting, okay? You normally first pan and then tilt, okay? Or maybe it's an integrated unit that directly gives you the top reference system that you have on top. And then let's call this top reference system where you have mounted the laser frame. So we have three reference frames: base link, the base, PTU frame, base link frame, PTU frame, pan tilt unit frame, and then there will be another frame on top, which is the laser frame that is mounted on the panel unit. We know it's to be, no? For each frame, you know where it's mounted on. The panel unit is on the robot, the laser is on the panel unit. Okay? Now, that's basically what you have. You have links and you have joints. And you can define the structure. There is a complicated URDF format that allows you to define the structure of your generic robot and of your manipulator. Essentially, what you're doing is to describing these kinematics, specifying, it's like a transposition of the Navier-Artenberg, where you specify for each link, which are the reference frames, where it is, and then if there is a joint between the two, how this joint, whether it's prismatic joint or it's a rotational joint, and so on and so forth. Now, all this information, in general, remember that ROS is bloated from this point of view if you work with this class of robots because there are no moving parts. But all these things, in general, this information flows over the network. What information flows over the network? The entire structure of the kinematics of my robot. Okay? So, all the links, not only the links, but also the transformations between the links, so the transformation that expresses the reference position of my panel unit with respect to the base of the robot, and the transformation that expresses the position of the laser with respect to the origin of the panel unit, all these quantities are broadcasted constantly over the network. That clear? Is clear what sort of data structure I'm talking about? Yes. I'm talking about a tree, where the root of the tree is in general the mobile base of the robot, and then on top I might have all other sensors which are playing with it. For instance, if we look at this horrendous, this was a Kinect version 1. If you look at this horrendous device here, no, it's not horrendous, it's the fantastic Kinect version 1 that had the brilliant optics. And if you look at this robot that was made with scavenging components, basically, we could identify several things. Now, there is some tradition in the ROS ecosystem of putting frames as they want. We have one thing which is called the base footprint. Yeah, because in order to make the things a little bit more complicated, we're not reasoning in terms of the base of the robot, right? The origin of the robot, and in case of a differential drive, is sitting in front of the axis, in the middle of the axis between the two wheels. This is where you put the origin of a unicycle. No other point there, right? There. Now, instead of putting there, because it was not nice, it was not on the floor, they put it on the shadow of the robot, right? That's a shadow of the robot on the ground, and so that's the base footprint, the footprint of your stamp. On top of it, given that it has to be a chain, on top of it I put the base link, right? And then on top of the base link, here we can see, but it's weird, here we could see a laser scanner, right? Now, if we wanted to be smart, and if we wanted to be adherent to the reality, we could observe that on top of this laser scanner, we put a Xeon. We put a Kinect. But if you look at the Kinect and the laser doesn't move. So I say, instead of putting on a laser frame, I just express a relative transform between this position and this position that I call Kinect frame, and I'm happy with it. Because if they are rigid, you really don't care about what is what, they are just rigid. Okay? Then now you construct the transform is useless. Now, imagine that every of these objects here, the base footprint with respect to the base link with respect to the Kinect frame and so on, could change its relative position because maybe it could be mounted on a joint and so on and so forth. So what we have is that there is a data structure, there is a system that allows you to determine the position of every point with respect to every other. And this occurs basically because there is there are a set of nodes which are in charge of outputting periodically, you see this broadcaster, outputting periodically the transform between one frame and its child frame. Clear that? Is that clear? There is an idiot that is constantly repeating the base footprint is 10 centimeters on top, on the bottom, no. The base link is 10 centimeters on top of the base footprint. The base link is 10 centimeters on top of the base footprint, like constantly at 50 hertz. Okay? That's, for instance. Of course, you could change the rate. It's not very smart. There is another topic which is called TF static, which takes the very same information, but you just say it once. But that's it. Okay? Now, what are these concepts that I have expressed are the so-called transforms. What are transforms? You remember that TF message that we have listed when we had, I think, stage running? Let's see. No. ROS CD, stage ROS. ROS run, stage ROS, vlog. This is the default package. Of course, you don't have a core. You have the core. Now, starting stage, it's loading. Takes days, but it has loaded. ROS topic, list. Oh, that's the thing which is called TS. Okay? This is the topic on which this data structure is periodically sent. Okay? Now, how do I see and how do I understand? How are these transfers made? Let's see. Echo TF. Okay. It's like it's an array of things. For instance, well, this is the header, this is the timestamp, this is a frame ID that goes from base footprint to base link, and then you have a translation and a rotation expressed in quaternion. So I'm sending out these three, one piece at a time. Every time expressing the position of the target with respect to the position of the reference. Agreed? And given that multiple people can publish on the same topic, I might have different actors publishing different portions of the transform tree. Because the topic is the same, but I'm publishing, for instance, the pan-tilt unit information, the pan-tilt links, and you're publishing something else. Is that clear? Very good. In this case, we have that stage is publishing. But this is very messy as way of reading the thing, so ROS run. There is a program of the package TF, which is called view frames. Guess what view frames does? Produces a PDF called frames PDF. And these are the frames which are produced by my machinery, my simulated machinery. We have odometry frame, we will see it later, base footprint, tradition, base link, base laser link. Okay? Clear? Very good. This is what I have. Of course, once I have a real robot, I will be the one responsible of publishing the transforms, right? I need to have an actor or some component that publishes this information. Otherwise, the nodes that are using this data, they don't know what to do with it. Is that clear? All right. Yeah. Now, how could you, in the simple case, if you want to be lazy and you want to waste a little bit of CPU, just because we have too many, what you could do is to launch a program that does exactly this challenging task that I've told you. You assemble your robot, you fire your sensors, you calibrate it, no? Because by calibrating you manage to sell it for 4,000 euros instead of 30 euros, right? You calibrate it, and then the calibration will give you a lot of things. It will give you the diameter of the wheels and so on and so forth. By the way, calibration is something that you don't do with the righello, with the ruler. You do it automatically, right? Because with the ruler, no, it's not the way to go. Automatically means by using these strategies like least squares and so on that are taught in some other courses by me. And anyway, what you could do after you have these numbers is to publish a thing, to have this little dwarf that constantly and systematically publishes a transform. Okay, guys? And what do you need to do? So a fragment of this tree. And what do you need to tell? You need to tell what is the link from, what is the link to, no? And what is the transform between the two. This program is called TF static transform publisher, and it's a member of the package TF. Okay? Now remember this transform tree that we have visualized some slide ago. I think here. No? Yeah. Where did I visualize it? Ah, here. Frames PDF, yes. This was the transform tree, and now I will have the humongous fun of starting another piece of program, this publisher, that answer, I don't know, Aula 41 on the base footprint. So we're mounting this lecture hall on the robot. Run TF static transform tab publisher from base link to Aula 41. And then the synopsis, of course, I don't remember it because you can't remember it, it's forbidden. The hertz, okay. Oh. Oh, mi sono perso il terminale. Ora qua. 0, 0, 0. 0, 0, 0. Just in the origin, no? Or 0, 0. 10 meters high. The Aula 31 is floating 10 meters on top of the robot. And let's publish at 200 hertz. Base link, target frame, and 0, 0, 0, 0. Probably because it has, what is the synopsis? Probably the first three are the angles. And the last three are the 10 meters. It's also smart. It tells me the two bodies are compenetrating each other. ROS run, TF, view frames. Listening for 5 seconds. Vince, frames, PDF. Vince. Probably the arguments, guys, sorry, the arguments of this ROS help. Oh, terrible. Help. Oh, XYZ. I messed up the transforms. So, XYZ, yo, patrol, what was it? Base link and Aula 41. Again, it's pleasant. I have to close this. No? No. Okay, guys, you understand that I'm not able to read the documentation. I should like just give XYZ, XYZ, yo, pitch roll. It's like more the Tigna that I'm going. Yo, pitch roll. XYZ, yo, pitch roll, frame ID, child frame ID, and period, right? So 0, 0, 1, 0 was missing. Terrible, I hate these things. And finally, we will see our complete transform frame. Oh, Finally, and then of course, probably somewhere else I had also, I didn't kill this transfer publisher that was publishing on 10, so I have a leg appended there. But yeah, that's it, no? Okay? Very good. So this is how you set up your robot. And at this point you can use it because every sensor knows, or every data knows where it's located. Okay, now let's move on. Now we are able to calibrate the robot. To visualize the data, once you have the data calibrated, also consider that if you go on RVs, you will be able to see consistent things because RVs takes care of, for instance, of where the laser scanner is located in order to render the data on it. But let's come now to a more juicy part, which is, okay, now I have set up this system, but I'm the one that wants to use it, these TF things and whatever else is needed, to, for instance, render a 3D point cloud of my lecture hall because I mounted on this little laser scanner a pan tilt unit. Okay, guys? Clear? Now remember that in all this game and in all this infrastructure, the word appears as an additional link, typically. So you have the word, and you have the robot in the word. And between the two, there is a transform, which has 3 degrees of freedom, x, y, z, and roll, pitch, and yaw, that expresses the position of the robot with respect to the word. Okay? And in this way, you would be able to map the robot, to visualize the robot, for instance, in the map. In general, all mobile platforms define a frame, the frame, which is the odometry frame, in a way that if you don't have any mapping system, at least you can anchor to the odometry frame, which is when you turn on the robot is in the origin, and then the relative transform is calculated based on the odometry running on the platform. Okay? That was this odom that we have seen before, like into this thing here. See this odom? Okay? And also remember that when you are rendering something on RVs, you have to specify on RVs what is the frame which is fixed, right? And so you could decide to have a robot-centric view, and then you say that the fixed frame, for instance, the base link or the base footprint, or you could have a word-centric view in which you set as fixed frame the odometry of the robot, or something else when it will be coming. Okay, but now from the programming perspective, what we're interested in is handling handling this issue, addressing this issue. I might have different sensors which are produced by different vendors, and then they operate on their own, let's say, frequency on clock. The only thing on which I can be relatively sure is the timestamping at which these data were. But I might have a pan tilt unit which is extremely slow, but maybe extremely accurate, that when I tell to this pan tilt unit, hey, please move from this location to this location at 1 degree per second, it's effectively doing that, but it doesn't send me any message until the end. Okay, or it sends me a message every 2 seconds or so. And maybe my laser scanner is moving like hell in between, right? And in order to construct accurately this 3-point cloud, I would need to know exactly at which point, at which inclination was my pan tilt unit in every point in time. Okay, right? So normally, how to handle that? You handle that with interpolation. If you know the kinematic model, the most smart thing that you can do is to send out not the transforms, or you can send out the joint locations, and then to delegate to someone to calculate the interpolated value of the joint positions, like in the position, then you generate the transform at the sampling time, and then you're done. This is actually what's internally done. All this mechanism of transform is handled for you by some facilities that ROS provides, which is the transform listener. What is the transform listener? It's a paradigm, it's a class that stays there. When you start the transform listener, says, hello, I am a transform listener, and it starts registering, it starts listening on the TF topic. Internally, it constructs its tree of transforms, like all of them. Remember that it receives only chunks of the transforms, right? Because from the TF messages, you only have from to, the position and the timestamp. It accumulates a set of buffers where it stores the temporary data, and then whenever you ask him, hey, please, can you tell me where is this location with respect to this other location at this time step? It calculates, it does the interpolation for you, namely speaking, and it returns you, if possible, the transform between the two frames. Is that clear? Is that clear, guys, or the message? Now, remember a second what we need to do for conducting an interpolation. If we want to interpolate at a certain time t, we need to know the position one instant before and at least one instant before and at least one instant after the time we want to interpolate, right? Because we need to draw a line. Basically, we are drawing a segment, and in order to calculate the inclination of the segment, we need to know where it starts, where it ends. So the height at the two positions, and then of course, the position before and the position after. You can also do some sort of interpolation in the other way, but so if you only have the position after, but if you only have a position before, but at least you need to have two positions before. In this case, we are talking about extrapolation, which is not good, and the extrapolation can be done before and after. All right. How to do this? How to use this device is quite straightforward. You can basically you declare an instant of an object. Okay, the object is called a transform listener. I don't know if with the new version transform listener 2, but my message is Google for transform listener. Okay, you declare this object. This object, when it wakes up, what does it do is that it inquires this global variable that ROS installs, and it subscribes to the transforms, okay, to the transform system. And then you take an instance of this object, and you can ask him two things. Two. The first thing that you can ask him is, do you have enough information to calculate the interpolation between this frame and this frame at this time? Where the frame IDs, if you remember, they are defined as strings, okay? So you know the frame name, because if you're listening a sensor data, it has written it into the header, right? So you have two frames, and you say, hey, can you tell me what is the position, for instance, of the laser with respect to the odometry at this point in time? And then the system, in our interpolation example. And then the system will calculate the interpolation. You will know at this point in time where was facing our LiDAR, and you will be able to draw the points at the correct inclination. That clear? But of course, if you don't have this mechanism holds on certain buffers, that cannot be infinite. You cannot remember all possible transfers that have been sent 3 hours ago. You have a limited buffer size, first. Second, you can't ask transforms that are not yet published. Even you better ask the transform a little bit after they are published, because otherwise you run into the extrapolation error. So you need to introduce some sort of lag into the system, which sucks, but you have to do it. Okay? Anyway, these are the synopsis of a transform listener. To create it, this is a constructor. You construct it. You tell it how long should it listen, and you can also tell him if it needs to run on a separate thread or if you want to handle it by yourself. Okay? Clear? Once you have an instance of this object, you can ask, hey, dear listener, can you transfer from this frame to this frame at this time? And then it says yes, fine. If it says no, you can read the error on this string that you potentially pass as a pointer. If you pass a null pointer, it just says no, and then basta. Once you can transform, first ask permission, then you can do the actual lookup. So you can query for the interpolation. And in this case, what you do is that you provide where from, so where to, so the origin and the target, and the time at which you want to know the transform, and then you also have to provide, here you have an ampersand, you provide a reference, a data structure which is called stamped transform. You could see what is a stamped transform because you have the tools now. ROS message shov sensor message geometry messages stamp no show tf stamp sensor, where is the stamp? Ah, transform stamped. Oh! Because they changed the name. Yeah, sorry. It's a transform that has a frame ID, a child frame ID, so in this way you realize the link, and then you have translation and rotation. Okay? That's it. So now, please don't refer too much to the slides, because this might be of ROS of 2 versions before, and now maybe instead of being lookup transform is transform lookup, but you know, the message is the very same. Okay? Now, another thing that is good, and then we will conclude the lesson soon. One thing that is good, that we will be doing is to record the stream of data, because what I have done before, normally, like when you work on a real robot, you don't have access to a real robot, not all of you, sometimes you don't want just to run on a simulator, but you just want to act from the sensor point of view as if you were having your robot in front of you. And a ROS system, basically, from the sensor point of view, just produces topics, right? And so there is a program that is made for recording all the topics, or a subset of topics, which are produced by a running ROS system into a file. And similarly, later on, you could take this file and play back all this topic on the network as if you were having the real robot in front. Is that clear? Very good. Now, there was a small exercise that I think we will revive. We will provide you, so these are pointers, look at it. We will provide you with a bag which contains the following transform tree, I think, or a similar one, where in this bag there is we have recorded laser scans and the position of the robot through the transform tree, where the position was acquired. What we're asking you is to construct a simple C program that just straightforwardly, each time you get a sensor laser scan, it calculates the position of the endpoints of the laser scan into the global frame and write them on a disk. Okay, X, Y, Z. Once you have done that, you could plot these points, which will be just X, Y, Z, X, Y, Z, or X, Y, X, Y, X, Y, X, Y, in case of a 2D map. You could plot it with glue plot and visualize the map of the environment. That clear? Okay, now don't, yes. This is the message, how to do it. The very first thing that you do is that you experiment with a transform. So you write a stupid node that every time it listens a laser, it interpolates the transform in the autumn frame and it writes down something. And then the second time you actually read the laser message and you accumulate the points in the global frame. I think you are all baked in class. You're losing attention like never. And I think at home they won't be much better, but let's see if I have some questions. Thank you, Antonio. Well, we will leave anyway. I have shown the messages already. I mean, I see that the guys have really, or the students have really, occhi bovini, no? Yeah, che vanno bioccato? They turned on the heating and now they are all relaxed. Yeah, you see? You see, there's a reason why you should be cold. All right, folks, have fun. And yeah, see you next time.